Okay, so since a couple of weeks, we've been talking about how the network, affects how people do things. Remember we talked about cascades last week, sequential decision making, how people get influenced by the previous decisions, and we explained that using Bayes' rule, remember that? Today we're going to talk about direct benefit cascade, other kind of cascade. This time, it's if you buy a product that everybody uses, this gives you benefit. If I buy Microsoft Word, because everyone uses Word, I get a benefit. I can exchange files. This is called direct benefit. It's also called network effects, which is kind of a very vague term, but I say it because it's kind of used. Okay? And we're going to analyze this. So we're going to do economics today. We get back to markets, and we're going to talk about stable equilibria, unstable equilibria, tipping points. Okay? People talk about a lot about tipping points in climate and global warming. When we get over tipping points, we're going to talk about tipping points today. And then next week we'll talk about another kind of cascade when something is diffusing in the network, and sometimes the network can block the diffusion. So we'll talk about that next week. So this is all different ways that many users can affect the individuals. Okay? And if we have time then, I'll talk about something else, which is rich get richer phenomena and the long tail. This is why Amazon is successful. So if we have time, I'll tell you why Amazon is making lots of money. Okay, so first I want to talk about direct benefit. Okay, so the point is individuals imitate others. Last week, in sequential decision, I imitate what the others do. Okay? And there's different ways. I observe other people. I get information, it influences my decision. That's what we saw last week. But there's another kind of influence, which is called direct benefit. It's, I want to do something, and I do it, and because other people do it, it gives me a benefit. So this is, I'm not looking at their decision, but what they are using, it gives me a benefit. So here's some history, fax machines, which are not used so much anymore, which was for sending messages. It only works. You know, a fax machine, you put a piece of paper on the other side, another piece of paper comes out, uses the phone, and it transmits the image. It only works if the people on both sides have a fax machine. Okay? So you only buy a fax machine if someone else buys it. Okay? This is a network benefit, a network effect. Or social network. I become user on the world's best social network, Facebook, and I only do it because my friends are on there. Because, of course, Facebook is a very terrible, and the leader of Facebook is a psychopath. Hey, Zook, how are you? Okay, so it only increases the value because there's other people on it. Or Windows, Mac OS. I use Mac OS not because it's good only, but because other people are using it. There's more software, okay? Same for Microsoft Office. So this is network effects. The fact that other people use it make it better for me. So that's what we're going to look at today. Okay? So this is economics. And if you want to do courses on economics, the economics people have a word for this. So this slide is just to make the connection with economics. Otherwise, it's not really neat. This is called externalities. An externality is where the welfare of an individual depends on other individuals. Okay? So a positive externality is like a direct benefit effect. If everyone has Microsoft Office, then I have a benefit when I buy it. This is called a positive externality. I get a positive effect. There's also, it can also go bad, because other people do it, things might get worse for me, like traffic congestion. The more people drive, the worse for me driving because there's congestion, traffic jams. And then typical economic detail, it has to be uncompensated, so a real positive effect. If I drink a can of Coke, it's not negative for the other people. There's one less can for others, but I'm paying for the can. So this pays for making another can, so I've compensated them. There's no uncompensated effect, so drinking a can of Coke is not an externality. So you have to get something for free, in a sense, a positive or negative thing. So the direct benefit effect is, in economics, it's called a positive externality. Okay, this is just for those who are going to look at economics. Okay, so we're going to use the usual way of studying this. We want to get really good intuition. What's going on here? We're going to define then an idealized model. This is our usual approach in this course, But today the model will be continuous. Remember in the previous lectures, usually the model is discrete. We have a network, and you have some graph, and you figure out what's going on. But today, where the model is going to be continuous, we're going to do a little bit of algebra with real numbers. We're going to make beautiful graphs, okay? And we're going to explain in 4 steps. So this will make it hopefully easy for you to understand what's going on. First, second, third, fourth. The first one is just the base. We're going to define a simple market economy, supply equal demand. Similar to what we saw before. Remember we saw market clearing. Before we saw it discrete. Now we'll see the same thing continuous. So that's just a simple market. In the second model, we will add network effects and see what you get. Okay? And this gives some kind of something called a self-fulfilling expectations equilibrium. People expect something to happen and it happens. So this is like the simple network benefits. But that's static. To really understand what happens, we have to see how things change in time. So that's the third model. We're going to extend it so we have things changing over time. And the way we do that is that the users think they get an effect, but maybe the real effect is not right. So the users are trying to fix the mistake. So the user is like always one step behind. Okay? The users correct the mistake, but the real benefit changes again. So this gives you a change in time. And this will give you stability, instability, and we'll show how it works. And the fourth one is the most complete one. This is where you have both individual and network. So individual means it's already good even if nobody else uses it. If I buy Microsoft Word, it's already useful, even if 0 other people are using it, because I can make documents and print them. But then you have, in addition, you have a network effect. So if you have both, this gives very interesting things. This gives kind of tipping points. You can jump from one equilibrium to the other. So if you want to make a company and make a new product, you have to understand this, and we show how it works for real products. Okay, so let's now talk about the first model. This is the simplest one. Okay, just a simple market. Supply and demand. But now we make a very interesting kind of continuous model with real numbers. So the consumers now in this model are numbered from 0 to 1. So each consumer is a number. 0.25 is the consumer, 0.26. And they're uniform. So the consumers are spread out from 0 to 1. Okay? And the interval 0 to x contains x fraction of the consumer. So from 0 to 0.6 has 60% of the consumer. This is a continuous approximation, because maybe you have 10 million consumers, but you make a continuous approximation. Okay? So the consumers are numbered from 0 to 1, and each consumer has a price that they're willing to pay. That's a market, they're buying something. The maximum amount they're willing to pay for 1 unit. This is called the reservation price, because maybe they're not really paying it, it's the maximum they can pay. It's the money they have reserved for paying. So that's R of X, okay? And since this is important, this is reservation price for consumer X. And X is a consumer, okay? And now the interesting thing is we're going to arrange the consumers in order. The consumers are from 0 to 1, but we're not going to put them in random order. We're going to put them in order of decreasing prices. So the early consumers are willing to pay the most. If the reservation is higher, then the consumer is before, X prime is before. So the reservation price will be a function that's going down, okay? So it looks like this, okay? Here you have the consumers, and all of them are named. They're all arranged here in a line from 0 to 1, and we're ordering them. So the ones early on, we're willing to pay more. Okay, so consumer 0.1 is willing to pay a lot. Consumer 0.9 is not willing to pay so much. So the Rx function is going down. Okay? Now, what's the price going to be? Okay, so this is interesting. We can see what happens when the price changes. Okay, first of all, everybody whose reservation price is greater than or equal to P. So P is the price of the product. It's the price of the latest and greatest iPhone, for example, market price. Everybody whose reservation price is at least that much will buy. Everyone whose price is less will not buy. So all these guys will not buy, but all these guys will buy. Okay? See how it works? And if the price is too high, nobody buys. If the price is greater than R of 0, that's the maximum, nobody's going to buy. If the price is less than R1, everybody's going to buy. You see how it works? Okay? So just to make it interesting, we'll assume that P is somewhere in the middle. It's between R0 and R1. Okay? R1 is less than R0. Huh? And there's a unique number. So we're assuming it's a continuous function. Strong assumption, but this will give us intuition. So everybody from 0 to X will buy. So the fraction of consumers that buy is X. Okay? Also, this is related to economics. So the function that gives me X as a function of P. So for a given P, I have an X. That's called the demand function. It's what percentage of people are going to buy as function of the price. So this is a simple kind of market, right? See how it works, huh? Okay. So, okay, assume that it takes money to make the product. P star. That's how much it takes. And there's lots of potential producers, manufacturers. So they're going to be competing with each other. Of course, they want to sell at a higher price. But since they're competing, we saw before that this causes the price to go down. Okay, so there's lots of producers. So the price will somehow stabilize around P star. Okay, that's similar to what we saw before. Okay, it's called the market price. And this corresponds to some fraction X star of the consumers buy it. Okay? It's very reasonable. You have to get intuition of this. Now this is an equilibrium. It means it's kind of a dynamic thing. So if there's fluctuations, it will always go back to this number. So if less than X star we're buying, maybe someday less, then there's going to be a few of them with a reservation price higher than P star. So they have incentive to buy. Okay? So if X goes less than X star, it has tendency to increase. But if X goes higher than X star, it will have tendency to decrease. You see that? Because if it's a little bit higher, these guys, well, they are paying more than they want to pay. Okay? So they're making a loss. So they don't want to buy, in fact. So if there's any fluctuation, it will always go back to X star. Okay? So this is really an equilibrium. Okay? So this is reasonable, right? This is something that you understand. So this is the beginning for us. We're going to now be adding stuff to this. Just another connection what we saw before. Remember social optimality. You're maximizing the sum of the payoffs of all the players, so the consumers are the payers. So we assume that all the guys less than X star are buying, and all the ones right are not buying. So that actually maximizes the social optimum. Okay? So what is the payoff? The payoff for a consumer, X prime, is the difference, Rx prime minus P star. So the payoff for some consumer here is this little difference. Okay? That's the payoff. So this whole left part, they all get positive payoff. This whole right part, they all get negative payoff. But we don't count the negative ones. We only count the positive ones. And we count all of them. So it's maximum. Okay? So over the consumers, if all the consumers less than X star they buy, we've maximized the social optimality. Okay? Because the ones to the right are not going to buy, of course. So for all consumers from 0 to X, it's the area between the two curves and the line, y equal P star and the curve. But of course, only the positive ones are going to buy. This is actually an integral. If you want to really make it technical, you have integrated. It's the area under this positive part. From 0 to X star, Rx minus P star dx. Okay, that's just making a connection what we saw. So market economy is maximizing social optimality. Okay, so that's the first thing. So far, no network benefits. Okay, this is our first model. Now we move to the second model. Now we add some network benefits and see what happens. So we change a little bit the model. Okay? So we will have now another market. We have two effects. Potential consumer will have two things. Their reservation price. Also, they will look at the other users. How many users? And so there's two functions now. The same Rx function as before. So each consumer has a maximum price. But now there's network benefits. There's direct benefits from the other users. There's another function, f of z, which is the benefit to each consumer when some fraction z has bought the product. So if 90% of the consumers buy the product, it gives me extra benefit of f of 0.9. Okay? That means the actual reservation price is not R of x, it's R of x times f of z. So it's the price they're willing to pay multiplied by the benefit because of the total number of users. So if you have more users here, then they're willing to pay more because they get more benefits. Okay? So this is a new model. Now we have these two functions. So let me put the second function here. So the whole rest of the talk, these two functions are very important, R and F. So benefit to user, if fraction z is buying. And so the user's reservation price is now not just R of x, but you have to add in the benefit. So f of x, we can say some things. F of x is increasing. The more people use it, the higher the z gets, the more the benefit. So f of z is increasing in z. Okay? It's logical, it's intuitive. Also, it's a multiplication here. It's not addition, because the benefit is relative. If I have some high intrinsic value, if I value this thing a lot, the extra benefit is like an extra fraction of it. Okay? So it's multiplied here, not adding it. See, that's also intuitive, huh? You have to get the intuition, huh? Also, let's assume f of 0 is equal to 0. For now. If nobody purchases, then benefit is 0. That's just simplification. At the end, we're going to make it positive in the fourth model. But for now, assume that if nobody is buying it, there's no benefit. Okay? Finally, let's assume it's a continuous function. So we can do nice real algebra on it. Also, let's assume that r of 1 is equal to 0. Let's assume that r goes down all the way to 0. Some consumers are paying very small amount. So that makes it more low, okay? So that is the new thing. So what do we get? So all consumers expect that z fraction will buy the product. And they know this is true number. They are actually z. So we're assuming this is the true number. Everyone expects z to buy. And what happens, in fact, in economics, is that if everybody expects z to buy, then the actual percentage who will buy will be z, okay? We can show that. This is called a self-fulfilling expectations equilibrium. If everybody expects it to be z, it will be z. Okay? So for example, if z is equal to 0, everybody expects nobody's going to buy this. Well, the reservation price will be 0, and nobody will buy it. See? Self-fulfilling. If you expect 0, it will be 0. If you have z in between 0 and 1, you assume some fraction is buying. Okay? So which consumers are going to buy? Well, if some consumer buys, let's say x prime is buying, then x, all the x that are less than x prime, they're going to buy too. Because r of x times f of e is bigger. The f of z is like a constant, that's the same. And this one gets bigger for small x. So all the consumers less will buy. Okay? That means the set of consumers that are buying will be going from 0 to z. Okay? And so the actual price will be the price that the stingiest consumer will pay, which is the one with the highest number. So RZ FZ is going to be the reservation price. Okay? So the price is going to be RZ times F of Z, the P stock price. So that's the difference from the previous model. Okay? So I'm going to show a graph, but first let's compare the two models. Okay? The first model, we have just market. The price is Rx star. The second model, with network effects, we have the price is RZ times F of Z. Okay? So in the first model, if you lower the price, so the price gets lower, more consumers are going to buy. Something like this. This is the R. This is the price. If you lower the price, you have more consumers are going to buy. Okay? Right? This is reasonable, huh? But with network effects, it's not that simple. Because you have this effect for everybody. We have to make a better analysis. You have to make some graphs. So we know that if z is equal to 0, nobody is going to buy. Because the reservation price is 0. But are there other equilibria? For the first model, it's easy. There's this one equilibrium. But in the new model, it's not quite so simple. We have to make some analysis. We have to look at these functions, R and F. What do they look like? We have to make some kind of assumption on it. Okay? So here, this is an important graph. Let's assume for simplicity, so we're getting intuition, okay? So I'm not saying that the real economy is going to be like this, but it's going to be kind of similar. So let's say that R of x is 1 minus x. So it goes from 1 to 0. And f of z is z. So the benefit is directly proportional to z. It's very simple. It's like almost the simplest you could do. Okay? So this is very simple assumption. R is decreasing from 1 to 0, and f is increasing, and it starts at 0. So f is going up like this, and r is going down. So rz times fz is z times 1 minus z. So that's this function here. It's parabola. Okay? So this is the consumers, and this is the reservation price. It's a function now that goes like this. You see why? Because the r function by itself goes down. But now we have the f. The f is doing exactly the opposite. So when you start, the f is very small. So this function, which is very high in the beginning, it's pulled down. Okay? So it's like this. Okay? So this is kind of parabola. Now this is actually a very neat kind of behavior. So that the maximum here is, for these two functions, it's 1/4. Okay? 1 over 4. So if the price is bigger than 1 over 4, there's no intersection. But if the P star price is in between, you actually have two intersections now. A low one and a high one. You have one with almost nobody using the product. You have another one with lots of people using it. And of course, 0 is also in equilibrium. So this gives us 3 equilibria. 0, z prime, and z double prime. Okay? And each of these is in equilibrium. If people expect z prime to buy, then there would be z prime buy. That's kind of neat, huh? But we're not done yet, because now we have a notion of stability and stuff. If we're at this point, is the system going to stay there? This equilibrium here, the old one, this one is stable. Okay? If the users fluctuates and goes a little bit less, it will go back up. If it goes a little bit more, it will go back down. So this one is stable. This is for the first model. But what about these two guys? Are they stable or not? That's a very interesting question. Okay? So we're going to talk about that. Stability, instability, tipping points. So now we get into some really interesting effects. Okay? Turns out, now we have 3 equilibria. I make them with circles here. So you have the 0 equilibrium and nobody's buying. You have the low one and you have the high one. Okay? Now, assume we want to see if they're stable or unstable. So we can reason. I'll tell you, well, this one is stable, this one unstable, and this one is stable. But we can reason it. Okay? So assume that Z is in here somewhere. It's there. What's the effect? Well, the reservation price is less than what they're paying. So these guys will be unhappy. So there will be less and less. You see, they are actually losing money. The ones that are buying here are losing money. That means less will buy and it will tend to 0. So that means if you're close to this point, you will go down to 0. That means this one is stable and this one is unstable. If it's in between Z prime and Z double prime, any consumer here they are paying this amount, and this is what they are willing to pay. So they have a gain. But even the consumers a little bit higher also want to buy, because they will also have a gain. So if you have a point somewhere here, all the consumers that are higher, they also want to buy. So this is like an upward pressure. So if the Z is in between, it's going to keep increasing until it reaches there. So this one again is unstable, but this one is stable. Okay? And so you have stable, unstable, and stable. So if you're a company, what do you want? Well, if you're in bad luck, you're here, and you go broke, okay? But what the company wants is to be there. We're a very high fraction of users, and it's stable. Oh, the company is very happy to be here. The problem is there's something in the middle that's preventing this number from increasing. If you have a low number of users here, it tends to go down. You have to go beyond this point if you want to reach the high one. You see that? So this Z prime is called a critical point. It's also called a tipping point. Yeah, it's like tipping in one direction or the other. If you're less than it, you go down to 0. If you're greater, you will go all the way up to the high one. And then everyone's very happy, okay? So you see, the network benefits gives you this very interesting structure. For Microsoft Word, for example. If nobody's using it, I'm here. But there's some middle part where I have to pay more, but there's still not enough people using it to really benefit from it, okay? I have to be here. So here I have a lot of users of Microsoft Word, and so there's lots of benefits. And so it's stable, okay? So the trick is, how do you get past the tipping point? Okay, that's kind of a thing, okay? Okay, so if you look at this graph, let me make it here again. So price, consumers. So this gives you this parabola, and here you have the P star. With the two equilibria. Now, you can change the price. So what companies can do, so if I'm a company and I'm in this situation, I want to get to the high one. But what can I do? Well, I can change the price. Okay, if I lower the price, so if I lower the price, for example here, then this number gets lower, okay? The critical point Z prime moves to the left, so it's slower and it's easier to get past, right? You see that, huh? The high equilibrium moves to the right, but the high one doesn't change very much, it stays high. The low one is interesting, okay? Now, if I lower the price a lot, if I set it below the cost of production, so it costs me, this is something that companies do sometimes, it costs me 100 euros to make an iPhone, but I'm selling it for 50 euros, so I'm losing money. But this is my strategy. That means I'm making the price low, that means this unstable point is closer to 0, so it's easier to get over it. You see how it goes? And I can assume I will get losses. But if I get enough people to buy it early on, maybe the price is low so people want to buy, maybe I'm making great advertisement, or I'm even giving them away, or whatever. As soon as I get over Z prime, I'm good. See that? Then I will converge to the high one. And then I make a lot of profit. And that will compensate the losses. So this is, you see, companies do this a lot, huh? And they do that exactly to get over this point here. You see that? So if you make a company, you have to remember that. This is something that companies do all the time. Free trials. We give you 1 month for free. Ooh, but after that, pay. Low introductory prices. Yeah, that's good. Actually, that's not a bad thing. It's just that they want to get more users so that everyone benefits. So of course they want to sell their product, but at this point, everybody is happy now. So it's a win-win situation. The company will make money, but also the users are happy. Okay? So this is the first lesson we get. So now I've explained this model. This is the first benefit. But this is a static model. There's no change over time. We're just assuming it's like this. Okay? So there's 2 equilibria, 3 equilibria. The middle one is unstable. And companies can move the price around to try to manipulate things a bit so they can get over that. Okay, so that's the second model. See how it works? It's very nice, huh? It's intuitive, huh? But it's static. It's actually interesting to see how things happen dynamically now. So let me make a third model where static is like everything's converged and it's fixed, okay? But let me see a model where things are fluctuating over time. But I don't want to write differential equations or something. I want to make a simple model where things are changing over time. That's the third model. Okay? So I want to make a model that somehow predicts how things are changing over time. Okay, here's one way to do that works very well. Let's assume that all the customers think that some fraction will be using the product. Everybody thinks 60%, but it's not really like that. Maybe the belief is incorrect. Okay? Everybody believes that Z are using the product. That means the reference price is Rx times F of Z. But the real number using it is Z with a hat. But this is kind of unknown, the real number in reality. See, so the customers kind of believe that some fraction. And they will purchase if this price is higher than or equal to P star. Okay? But that's not how many will really, okay, purchase it. So if you want to know how many are really purchase it, this is what they want to do, okay? But the real fraction is going to be the number that makes this equal to P, okay? So R times Z hat. Z hat is now the real fraction, and you can compute it, okay? It's like a correction. With this equation, you can do like a step forward. Okay? You think, I want to purchase of this, I think it's Z, but actually the real number is different, Z hat. But if I solve this equation for Z hat, it's inverse of R, so it's R Z hat equal P star divided by FZ, and inverse of R. So it's this function. So the customer is like, they're behaving inconsistently. They believe it's Z, but they're using this equation. But this equation is not actually consistent with Z. The equation is consistent with Z hat. So that means it's kind of like an iteration. So there's a shared belief, Z. We figure out the real fraction, Z hat. And then after that, everyone is going to realize, oh, but actually 70% used it. But the situation has changed. So the next step, everyone believed would be 70%. And then again, there's an iteration. So this is kind of, the customers are trying to correct their beliefs, step by step. Okay? It's a way of making it go step by step. Okay, we can actually make the computation. It's not hard. The intuition is a little bit funny, but I try to give you the intuition. Okay? we can actually compute the z hat, and we can show what happens. And we'll see this step-by-step behavior. Okay? So it's actually very easy to compute. So the function r is continuous and goes from 1 to 0. And a solution exists if the p star over f of z is actually less than r0, right? There's an intersection. So we define the function g, which is this inverse. Okay? When it's existing, otherwise it's 0. Okay? Now we can actually compute this. The inverse of r is 1 minus x. So r is the function 1 minus x. But what's the inverse of 1 minus x? It's also 1 minus x, huh? If I go from 0.2, I go to 0.8. But 0.8 goes back to 0.2, so that's also 1 minus x. Okay? So if you put it in there, you get 1 minus this, and f of z is still z here, right? It's linear. So the function g is 1 minus p star over z. But only when there's an intersection, otherwise 0 will be using it. So the curve looks like this. Okay, it's 0, but here, this gives me this is the expected fraction. I think it's z, but the real fraction will be this, according to the function. So if I think it's 60%, then I see, no, the real fraction is going to be 70%. Okay? But this is, so why are we doing this? Because now we can iterate. Now we can go step by step. Okay? But first, let's explain a little bit this diagram here. So the expected fraction using the product and the real fraction. Okay? And we have this curve, but we also have the line z hat equals z, 45-degree line. So the intersection, this is when z hat is equal to z. It's like this, these are the stable points. Okay? These are, again, the equilibria. Okay? When I'm less than z prime, okay, here, actually, the real fraction will be less than the expected fraction. That means consumers will be disappointed. They think 50% is using it, but it's only 20% or 0%. So in the next week, they get disappointed, so the number goes down. But in the middle here, they think it's 40%, but it's really 60%, so the consumers say, hey, this is good. More people are using it than I think, so they will be happy, and there will be more people using it. And if the fraction is too high, then again the consumers will be disappointed, okay? Because the real fraction, z prime, is less than what they think. So you see this one is a stable point and this one is unstable. So it's another way of seeing this stable, unstable. But now we can do dynamic. We can do things dynamically. Okay? Let me show you how it works. So first of all, this is the curve that we get. But in real life, it's going to be more continuous curve. Okay? So in a more realistic situation, it's not going to be a break here. It's going to be more continuous. So it's going up and then it's going down. Okay? So the curve will sort of look like this. This part is unstable. Expectations. This one is stable. Okay? So again, we have the two equilibria. But now we have a step-by-step version. We have today's knowledge, and we have next week's knowledge. You see that? I expect, the consumers this week expect to be 50%. Next week they see, oh, it's really 70%. So that is the next week knowledge. And then we can keep iterating like that. Every week we will iterate through this curve. Okay? Okay? So we can now actually use this curve to see what happens over time. So here's a scenario, okay? Now I'm not talking about markets, but I'm going to talk about social networks, social media. So you can think of this also in terms of social media, okay? People they're on Facebook, and they evaluate their participation on Facebook. And every person has an intrinsic interest in using the site. Why they're interested in it, R of X. This is like the price, huh? The site's attractiveness increases with more users. So that's the benefit, F, you see, okay? And then there's the amount of effort required to use the site, and that's kind of a price. You have to do something, some effort. So you can actually look at social networks in this way. So maybe person X expects so many people, Z, participates, and X will participate if the benefit they get is greater than the effort they put in. That's logical. And now time is going forward. Okay, week by week. T is 0, 1, 2. First week, initially we have C0. But what happens then? Second week, third week. Okay? So at time T0, you have Z0. Okay? In each time period, people are expecting the audience size to be the same as it was before. People usually will think that things are going on as before. Okay? So, assume that Z1 is G of Z0. Okay? People expect Z0, but the real number will be Z1. Okay? But then the week after, people go, actually, no, it was Z1. Everyone will now expect Z1. After 1 week, they see it's Z1, but it's really Z2. And then the third week, they will expect Z2, so they will always expect what it's going to be, what it was the week before. Okay? So this is kind of approximation now. We're assuming people are being kind of stupid, myopic. They expect the future to be like the past. Usually people are like that. It's raining now, in 10 minutes it will be raining, but it's reasonable. So this will give us something. So people expect C0, but the real number is Z1. And then people say, oh, actually it's C1. The week after they say, we're smart, we expect C1, but the real number will be Z2. So you will be iterating this function, see, step by step. The expectations and the reality. And the reality becomes the expectation for the next week. And this gives something like this. Okay, so this is our curve. So here on the horizontal we have the expectations. Here we have the reality. This is the curve I showed before, right? And this is the 45-degree line. So we're doing Z1 is equal to G of Z0. Z2 is equal to G of Z1. We can do it graphically. So assume we have a Z0 here. Z0. So this is Z0, Z0. We go up here. This gives us Z1. If we go now horizontally to this middle line, you get Z1, Z1. You see that? And now we can repeat. So we have a path. Like snaking along. See how it works? You can graphically follow the behavior. So we have these zigzag paths. So this is actually a very nice way to look at the time behavior. So 0, 0, 0, the expectation is Z1. We go horizontally, we get to Z1, Z1. And then the next week, it will be Z1, Z2. So we go up again to intersect. And then we go horizontally. So we're always going up and then horizontal and zigzagging. And then we see what happens. So this one is going to converge to that point. Whereas if I'm here, it's going to converge down to 0. Okay? Whereas if I'm very high, I follow it, it will converge again to that point. So you can see the high one is stable. The expectations are converging. Whereas the low one is unstable. This is expectation is not converging. See how it's working? So here we can see evolution of time. Okay? And now we can see how companies are going to do it. Okay. So now I want to show you how companies are doing that. Okay, so let me make a break. So this is good. So you have to understand how it's working. Expectations, reality. And then the reality becomes the next expectation, and then we have a new reality, and so on. Okay, step by step. And if you can then follow the behavior over time. Yeah?
Does it correlate with the swine cycle? Or
the what cycle?
there is a cycle that with I forgot the word.
In economics, you mean, or what?
Yeah, it's a social, it's not purely economic, but it's basically you have swine, you start to breed swines because they are in demand, and then you have too many, and then you need to kill them off, but then you don't have enough to...
This is more like, what you're thinking of is more like population dynamics. How the population grows, you have too many swine, and you have to kill them off, so then the number goes down again. Yeah. But here it's not, no, it's a different thing actually. Here I'm not worried, the population is not changing, but there might be a connection. I'll have to look at it. Okay. But the swine thing, it's like population dynamics, where the population grows too much and you have to make it go down again. Whereas here, so that one could, when you're saying it could oscillate down.
Yeah.
Whereas this one is not going to oscillate, it's going to converge. Okay, but there might be some connection, but I'll look at it. Okay.
Thank you.
Swine cycle. So it's swine like as in pig, right?
Yeah.
Okay. Okay, so that's all. We're in the break now. So let's set up also. So let me go on now. So now you see the dynamic behavior here. Now this graph is very similar to this one. We still have the stable and unstable one, but with this one we can actually follow the evolution in time. We can see how it converges. Whereas this one, all we can say, it kind of tends to go to the intersections. We don't know how much or how fast. So this is a kind of way of seeing how it evolves in time. Okay, before talking about the final model, this is the one where even with no users, there's a positive benefit. This is going to be the most clever one. But before that, I want to talk a little bit about how companies, what happens in real life with this stuff. Okay? Okay, so I'm a company. I want to sell a product and the product has network effects. I'm Microsoft. I'm selling software or hardware or social media. So in the old days, I'm talking 15 years ago, there was a social network called MySpace. And then there was a new guy called Facebook. And they were competing. So I will not succeed until I get past the tipping point. This is what we saw in both the second and the third one. So if you just want to start small and you hope that you grow, that's not going to work. Okay? And people are not going to come knocking on your door. No, it's not going to work. You have to convince a large initial group. Somehow, you have to convince a bunch of people to use your thing. of your product. Maybe you give it away for free, or maybe you do something that gets people. You have some media blitz or some viral campaign or something, and a bunch of people buy it. So you may get losses, but if you get past this point, then you're good, okay? Then you will converge, then you're fine. You will converge to the high equilibrium, and you're in a good position. And hopefully, once you're at the high equilibrium, you can make profit and overcome the initial losses. So you need investors who are willing to pump in the money and lose money first, okay? An alternative is you have influencers. There's these influencers. For some weird reason, they have a lot of influence. Fashion leaders. And if they are using your product, others will use it. Okay, this is something we look at. It depends on how connected they are in the network, these influencers. Do they have a lot of connections in the network? And then maybe they can influence and help you get over the problem here. Okay, so that's what you have to do. You have to convince a large initial group. So remember that. And if you make a lot of money, remember your professor and give me some part of your profit. So also another thing, social optimality doesn't work anymore with network effects, unfortunately. So if there's no network effects, the equilibrium is socially optimal. We saw that, it's the maximum. But if you have network effects, it's not true anymore. So social optimality means that you have the sum of the payoffs is maximum, okay? But it doesn't work anymore with network effects. Suppose we have an equilibrium, Z star, I'll show you how it works. Okay, and the reservation price of the one at Z star, so the highest consumer is this, R times Z star, F Z star is P star. Now, assume you have consumers a little bit higher, from Z star to Z star plus C, a little bit more. They don't want to buy, of course, because their reservation price will be less than P star. They don't. But if they did, all the consumers' payoffs would increase. So you can't just add up the payoff from the new consumers. If these little new consumers come in, all of the consumers, because all of the consumers have this factor, and the factor would change. Instead of FC star, it would be FC star plus C. So if you add a few consumers, you're not just adding the payoffs from them, you're improving everybody's payoffs. So social optimality is not so easy to compute, okay? So, but there is a general principle. If you have network effects, then you will usually have less of the good that is socially optimal. So somehow the network effects are compensating for the social optimality, okay? So the network effects is kind of not social optimal, okay? And here, and a third point, this is something that happens in real life. Suppose you have many companies and they're competing. You have IBM, Microsoft, other companies making software in the 90s. Who dominates the personal computer industry? And then a very old one, VHS over Betamax. This is a very old thing. Videotapes. Have you ever used videotapes? In the 1980s, there were two standards. So which one is going to win? It's not the best one that's going to win. So the point is not to be best. The point is to be the first one that gets over the tipping point. The first one that manages to make this jump, it's going to win, even if it's technically worse. Okay? Being first much more important than being best. Okay? Okay, so what can you do? If product A now is somehow dominating product B, and B is licking its wounds and saying, what can we do? Because A has won. Well, maybe there's still some possibility. If product B is enormously, massively improved, and A does not change, maybe you can still convince people to go over the tipping point for B. But it's much harder, okay? Long shot. It's much harder. Once the first one gets over the tipping point, almost surely, unless they are completely stupid, they will be the winners. Okay? So that's a thing. So this tipping point is a very important thing. Okay? Okay, now let me introduce the fourth model, and we'll see a little bit more subtlety, how you can do strategies. The fourth one is kind of the smartest one. In the previous models, we assumed f of 0 is equal to 0. That means if we have no users, the product is useless. Okay, there's no benefit. But that's kind of exaggeration. Because usually the product will have some use, even for the first user. So let's assume f of 0 is greater than 0, and not equal to 0. And we keep the property that f of z is increasing. But it doesn't increase from 0, it's from some number bigger than 0. And this will give us a little bit different graph. And will give new phenomena. So the behavior is a little bit different. We can get a new stable equilibrium that didn't exist before. So there's going to be a new stable equilibrium coming in. Okay? And it gives us a new way of getting over the tipping point. Okay, so how does it work? So again, let's make a kind of simple assumption. Let's assume a simple function. 1 plus az squared. Okay? Which kind of goes like this. And it starts off at equal to 1, and it goes higher. And r of x will still be 1 minus x. Again, let's look at the expected fraction and the real fraction. So the real fraction z hat is equal to g of the expected fraction. And we can compute this. So this one is not hard. We can do it as before, and we get this function now. 1 minus p star over 1 plus az squared. So instead of a z here, we have 1 plus az squared. So this is a different function. We're starting now with utility even for 0 users. So now we get this kind of a graph. And now it's actually really neat. Because the graph is now still kind of going like this. So we still have a tipping point here. We still have a high stable point, but we have a new stable point, a low one here. Because you start off greater than 0, so you will intersect here. So this one also is stable. Okay? So if you start your company and you sell stuff, you will go here. So you still will survive. You won't be at 0, you'll be at higher than 0. Okay? And you can still try to get over the tipping point. Right? It's still the same, but at least you will be here. So if your product already has some use, you will have a low stable equilibrium already. But you still have the tipping point. But now, you actually have a new technique, a new trick. So what you want to do, of course, what you want to do is you want to go from here to there. You want to go over this one. Somehow you have to get beyond that. And it seems very hard, huh? Because all the parts here are unstable and will go back here. So somebody has to get over it. But now there's another trick you can use. Assume you lower the price. So you have this function, So the function is here. This is the price. If I lower the price, it's minus. This function will be bigger, right? If I lower the price, the function will get higher. So what does that do? It's actually very neat. So if I lower the price slightly, maybe to Q star instead of P star, we get a new function, H, of Z, let's call it H, which is higher. But if it's high enough, it's not going to intersect anymore here. See that? The previous one intersected, so it's not going to intersect. At some point then, this function H no longer intersects the line Z hat equals Z. At this point, you're in a very good position, because there's only one stable equilibrium left, which is the high one. So if you're in the low part, what's going to happen? Well, if you follow the zigzag, you will keep going up and up and up and up and up until you reach the high one. So you're very good position. Okay? Now, what happens to the former unstable tipping point? It turns into a narrow passage. Now, this part is going to be like narrow. What does that mean? All that means is that it's going to take make longer time to get past there. You see how interesting it is? Before the tipping point, you will go back if you don't go over. Now, you will keep going toward, but it will be very slow. But once you get past the narrow passageway, you will go faster again. This might take a long time if the passage is narrow, huh? But it's still going to go up. You see, that's a neat technique that companies can use. Huh? So this passageway, it used to be the tipping point, but now it's just a narrow passageway. So the trick is, you start with giving the product as much usefulness as you can for zero users, and you reduce the price, and if you do it right, you will get rid of the tipping point. And the narrow passageway, of course it'll take time. And of course, it's not a miracle. This is going to take some time to get through here. But your competitors are not going to stand still. If they see you doing this, they might react to this, okay? So it's not an instantaneous miracle, but it's a technique, okay? So this technique can be used. See how it's very interesting to do this kind of mathematical modeling, huh? How it can give you insight, huh? Okay, so let me end with the network effects, and then we'll go to power laws. So we did 4 models, step by step. So you have to understand the step by step. So the base case, supply equals demand, then the static view of network effects, then the dynamic view, where you have the steps going up, and you can see what happens with the tipping points, and then the final one where you have both individual plus network effects, value for the first consumer. And sometimes you can jump to the high one through a narrow passageway. So this is something that really exists in the real world, okay? So this is something that now you can kind of understand it with the different models. Okay, let me now go to the final thing we're going to look at today, which is rich get richer phenomena, power laws. So previously, we're looking at how people are connected. But now, let's make a step in a different direction and look at popularity. How can somebody get popular on the network? Okay, in the previous things, we have person's decision depend on the choices from other people. Okay? But now, this is because of the network. Now let's look at the notion of popularity. Which people become popular? Okay? And it's very interesting. You have really extremely popular people and also less popular. So many people get wide recognition in a certain area. Some people actually get global name recognition. Probably there's very few people in the world who have never heard of Barack Obama. The guy has got global name recognition. Whereas Linus Torvalds is also famous, but maybe it's not global in a certain area. Huh? You know who it is, of course, huh? So how does it work, this popularity? This is actually really neat too. And it's also really the network which is doing it. And let me study now the web. So the web is a good example of an organically grown graph on a network. And we can measure popularity. Let's say popularity of a web page is the number of inlinks. How many people are pointing to it? So a page with 1 million inlinks is more popular than a page with 1,000 inlinks. And then we have a question. What fraction of pages have k inlinks as a function of k? How does the popularity, how is it changing? How many fractions have a certain popularity? And this is kind of really interesting, the result, and it gives rise to very important conclusions. So the result of this is why Amazon is successful. Okay, we'll explain it. And it leads to what's called power laws. Okay, so let me start with a naive thing, a naive model. Okay, we're looking at the web page. We want to see how many inlinks there are. Okay, assume it's going to be like Gaussian. Okay, yeah, there's going to be some distribution. Well, we can guess it's Gaussian, where you have a mean and a standard deviation. So the density is this function, which you've seen. Mean is mu, standard deviation is sigma, and it's ubiquitous, of course, because of the central limit theorem, which you have heard of, right? Théorème de limite centrale says something, rings a bell. If you take any number of, a large number of independent quantities and you add them together, no matter what their distribution was, the result will be normal distribution, Gaussian. So it's very natural, right? It occurs in nature. Well, right? Well, assume now for web pages, every page decides independently, randomly, whether to link to some other page. That means the number of inlinks will be the sum of many independent random quantities, right? Each page decides whether it points to you or not. That's a random thing. And you add many randoms, so you get Gaussian, right? As k grows large. That is totally wrong, okay? That is completely contradicted. This does not apply at all, whatsoever. It's not Gaussian at all. So somehow we have to try to figure out what's going on. So the fraction of web pages with k inlinks is proportional to 1 over k squared. So it's not a negative exponential, huh? And it's pretty much a square, but this number, sometimes it's even slightly bigger than 2. It's very weird. Of course, 1 over k squared, when k increases, it goes down very slowly compared to e to the minus k. Yeah? E to the minus k goes very quickly, very close to 0, whereas this one is very going down very slowly. So even if k is 1 million, k is 1,000, this will be 1 over 1 million. It's still bigger, a lot bigger than 0. This is called a power law, because it's a power of k. Here it's power minus 2. Okay? So it's not exponential, it's power laws. So power law distributions are very common in popularity study. So normal distribution is what you see in science when you measure something, like the weight of a fox. You know, it's normally distributed. But in popularity, you don't have that. You have a power law. And every time you look at popularity, going to get a power law. And there's many examples. The fraction of telephone numbers that receive k calls per day. So the more calls, the more popular, 1 over k squared. The fraction of books that are bought by k people, 1 over k to the third. The fraction of scientific papers receiving k citations, 1 over k to the third. All power laws. Any kind of popularity will be a power law. And it's very easy to test, of course, huh? If you want to know if the distribution is power law, a over k to the c, just to make a log-log graph. So you take the logarithm of that, and you take the logarithm of the other side, you get log of f is log a minus c log k. So that's a straight line. So if you make a log-log graph, and it's a straight line, then you have a power law. Okay? So here's a famous graph. This is for web links. Okay? So this has been measured a lot. So this is one measurement. Here's the number of pages. It goes up pretty much. Log of log. Yeah? 1, 10, 100, 10 million, 100 million. It goes up to more than 100 million. And here's the in degree. It goes all the way up to 100,000. Log. Notice it's pretty much a straight line. There's some fluctuations here when we get to the very, very popular pages. So there's a very small number of pages, kind of fluctuates, but it's pretty much a straight line. It only breaks down for a small number of pages with very, very, very high degrees. How come this line is so straight over so many orders of magnitude? It's kind of mysterious. So what's going on? What is the process? So this was a big question when the web was getting very big. How can we explain it? We need a process. The Gaussian, there was a process. You have the sum of many independent random things. What's the process here? Okay? Well, there is a process that explains it, which is called preferential attachment. And one way of calling it is, you can call it the rich get richer model. You'll see why it's called like that. So there's motivation. So I'm going to explain to you how this power law comes around. So as we saw, the normal distribution comes when you average out many independent decisions. But power laws come from correlated decisions. The decisions, again, are depending on each other. Remember, this is like cascades, huh? The decisions are depending on other decisions, just like a cascade or network effects. So the network is what's doing it, okay? So correlated decisions lead to power laws. So how does it work? Okay? Well, there was a simple model defined called preferential attachment. And if you study it, you immediately get a power law, and it seems to model closely what happens in the web. People have a tendency to copy decisions made by people before them. This is what we saw for cascades too. People will look at the previous one. Here it's also true for popularity. So here's the model. Okay? Assume now we're creating the web pages. We start by having 1, 2, 3, up to a billion or something. So you create them in order. Whenever you create a page, you make a link to an earlier page. So you create the new page, it links to one of the previous pages. Okay? But there's two ways it can do it. Either A, it chooses a random page uniformly from all the previous pages and links to that. That's like the Gaussian thing, right? It just picks a page randomly. But there's another rule. Instead of choosing a random page uniformly, you choose the random page uniformly, But you don't link to that page. You link to the page that that page is pointing to. Okay? You pick a random page, you look at that page also has a link. That is the page you point to. You take like one extra level in direction. You're linking to the page that that page points to. And you choose these two with some probability, yeah? P or 1 minus P. So this defines a single link from one page. Of course, you can repeat to make many links, huh? So look at this model. A is like the Gaussian thing. B is the special thing. B is the key. The author of the new page will in fact copy the decision made by the earlier page. Page J will read page I and make the same decision. That means if some page is very popular, then it's very likely you will pick a page that points to that popular page, and you will make it even more popular. Okay? And you can show that with this model, the fraction of pages with k links is proportional to 1 over k to the power of c. And c is some complicated function of p. Okay? Depends on the probability p. So this is called rich get richer model. So how come it's called that? Well, when you copy the decision of a random page, if that page, if there's some very popular page, then a lot of pages will point to that page. And when you pick a random page, you will very likely get a link to that very popular one. Okay? The more pages that link to M, the bigger the chance you will hit on a random page that links to M. Okay? So you could say it's like this. Page J chooses page M with probability proportional to M's current number of inlinks. So pages with large inlinks will get even more inlinks. Pages that are rich will get richer. Popular pages will get even more popular. That's very intuitive, huh? Someone who's popular will tend to get even more popular. If I have 1 million links to this page, then pretty clearly there's going to be many more links coming in compared to a page with only 10 links or 5 links. Okay? So a page's popularity grows at a rate proportional to its current value. So it's actually exponential over time. A page that actually gets a small lead, it's a little bit ahead of another page, will extend that lead. Small differences will be amplified. Here, compared with the independent variables. The independent variables, the differences are canceled out, or averaged out. Here, the differences are amplified. Okay? And this kind of growth, it's actually everywhere. Any kind of an organic, anything in the real world where you have a popularity, in some sense, is going to be like this. Here's another example. The fraction of cities with a population k is proportional to 1 over k to the c. There's a very small number of very populous cities and a lot of cities with a small number of population. Or the number of copies of a genome, which is very weird. Why would that follow a power law? It also follows a power law. Some genes are very popular, others are not. Okay? So this is in some sense very weird, huh? It means that things are unpredictable. When you start, again, if you want to become popular, then you have to understand this. The initial phase is fragile. In the beginning, when you're not popular yet, you can have random fluctuations. But once you become popular, you get even more popular. But then it's robust. So in the beginning, it's very fragile, the popularity, yeah? Because you have random fluctuation. But once you get popular, then you you will get even more popular, and so it becomes robust. Okay? Worse technology can win because it reaches a certain size before its competitors do. So this reflects, again, the tipping point idea. It's a kind of tipping point. Worse books. So, for example, Harry Potter books, very popular, millions and millions, 100 million copies have been sold. J.K. Rowling is a billionaire, okay, because of that. Even shows she was very poor when she was young, okay? She became a billionaire. Now, if we would repeat history in the early days, when Harry Potter was not popular, there are other children's series, okay, of children's books. Would Harry Potter be the one to become popular, or would someone else, some other children's fiction? In the early days, when Harry Potter was not popular, it was very fragile. But once it gets very popular, it's more. So this has actually been experimented with music. So here's an experiment. Music download. You download obscure songs, 48 songs. And it was done with 8 parallel sites, randomly. Okay? And they start identically. Because of randomness, it starts fluctuating. Okay? Which one is most popular? And it turned out the market share was fluctuating a lot, but the best songs still tended to be higher up, and the worst were still kind of low down. So there's still some kind of a quality. Quality is still important, but randomness is also very important. Okay? Popularity. Okay? So this is connected to information cascades. It's connected to tipping points. It's connected to cascades. Okay? So remember what we saw before. People aware of early decisions would end up in a cascade. So preferential attachment is kind of like a cascade, where the later web pages are doing the same thing as the early ones. But it's not quite the same. There's some differences. So there's many possibilities, not just 2. So you only look at one previous one, not all of them. You only pick one page. And there's no rationality. It's pure randomness, in fact. In the cascade, information cascade, it was because of rationality. Here, it's random, but still, you have this effect, okay? Effect of the power loss. Okay? So this is still kind of not so well known. Rationality. How much is rationality important in web? Those people don't know yet. Or information cascades, are they also doing power laws? Okay. So there's still a lot of unknown stuff in this, Okay, the final thing I want to talk to you about is called the long tail. So the long tail, so in French it's called la longue traîne. This is how we connect popularity to economics. Okay, so let's say you have a media company, a company selling books or selling music. So there's a question. Where does the company get the sales? Where does the profit come from? Does it come from the hits, a small number of very popular items, or a large number of less popular items? So there's 2 possibilities. Maybe the company gets rich because of hits, a few hits like Harry Potter books, or maybe the company gets rich because of niche products. Huge number of kind of unknown products, like a supermarket. The supermarket can have 10,000 products, and none of them is really very popular. So because of internet, we go to this one, to niche. So if you have stores, brick and mortar stores, then you tend to have hits being the one. Because stores are small. They don't have so many possibilities. Because internet commerce can have an enormous number of products. You can get millions of products, much more than a real store. So because of internet, the long tail of obscure products is what drives things. So this is actually really interesting. A lot of obscure things, which before were kind of disappearing, no one saw them, now they are brought up and making things very successful. So look at Amazon or Netflix. Amazon is very successful nowadays. Wasn't always like that, but nowadays it has millions of products that you can choose from. Huge one-stop shopping, okay? But it doesn't need to have all that inventory in a store. They have what's called these distribution centers, which are huge warehouses, but they don't need so many of those. And they can be used by anybody at home. So it's like supermarket, but on the internet. This is actually why internet commerce is very successful. It's one of the main reasons. And it's called it's because of the long tail. So here's a graph. Okay. So this is selling books. So here I have how many books are sold. So here I have a few books, and here is the books, and here is the popularity, the sales volume. So here we have a small number of books that are very, very, very popular. So those are like hits, okay? But the unpopular books, so with very small sales, they're here, this goes up very much. How do you compare this profit coming from this or here? You see, you have a small number of books with huge volume per book, or a huge number of books with a small volume per book. So if you have a bookstore, then you're here. But on the internet, you're on the other place. Okay? On the internet, you switch the graph around. So here I have now the sales volume. Very low sales volume. The books, 1 or 2 or 3 books are sold. But the number of books, the different books, you have lots of books, and each book only has a few buyers. Okay? So this goes on very, very long. And it goes very long because this graph is a power law. It goes down very slowly. So you can have millions of books here. It goes down very slowly. And the total aggregate sales of the unpopular books can be much bigger than the sales from the hits. Okay? And this is why Amazon is so successful. Because they are selling huge numbers of unpopular books. So I love it, of course, because I love looking for certain kinds of unpopular books. Okay? And they're very hard to find. But on Amazon you can find them. Or on eBay, or on whatever internet commerce. Okay? So this is called the long tail. It's long because it's a power law, and it's the basis of internet commerce. Okay? The success of internet commerce is depending on this. Okay? Okay, so let me summarize. So the web page popularity is following the power law because web pages are correlated, and the model is called preferential attachment. It's a rich get richer phenomenon. The popular pages get even more popular. The millionaires get even richer. Okay. Initially it's very unpredictable, but once you start getting more popular, it becomes robust and it grows exponentially. And finally, the long tail, a power law decreases very slowly. Question? Yeah, it decreases very slowly. So if you have a huge number of unpopular pages, the total popularity of millions of unpopular pages can be higher than the popularity of a few very popular pages. And web commerce, much success, depends on that. They have a huge inventory, but they don't have to stock it all into a single brick store. Okay? It's on the page, on the page. So this is one of the reasons for the success of web commerce. Okay, there we go. Question?
So, does that mean that if I just have a few products that are very popular, and then I'm doomed because
if you have a few products that are not popular, you're not necessarily doomed. But if you would create many variations of your products, like let's say you're selling windows or doors or whatever, if you have many sizes, hundreds, thousands of sizes, on the web, you don't actually have to have inventory for them. You can sell them and fabricate them on demand, and people can see pictures. Then you will be much more successful than if you had only a small number. Yeah. So you see lots of variations. You know there are sites where you can buy shirts, and you can customize them in a million different ways. Maybe you've seen those. And so they don't have a million shirts in their store, but once you make the order, they have a machine that makes the shirt for you. So you have millions of possibilities. And this is a huge push, I think, for success. Okay? So if you want to have only a small number, you're shooting yourself in the foot. Okay?
Does that also apply to donations? Meaning that if I ask for a small donation, I'll get more in total than if I ask...
that's a good question. Donations. If you're asking for donations for a good cause. Yeah. So this was one of the reasons for this was a famous thing. One of the reasons for the election of Obama in the long time ago, 2008 or something. So he had a lot of funding, and it was coming most of it from small donations on the internet, because millions of people gave small amounts of money. So this gave a huge funding for the campaign. And that's something that you cannot do except on the internet. Okay? So the internet, the small things are much more valorized, given prominence than big things. It's a big equalizer in that sense. So that actually is one of the good tendencies of the internet. There are bad tendencies like polarization, but this tendency is actually a good tendency. It causes many more things, small, unpopular things, to become valorized, become useful, and to be sold all over the world. Okay, so if you have some very niche product, very, very niche, nobody is interested in the thing you're selling, some weird thing. Well, if you sell it on Amazon, you could sell all over the world, and you could actually be very successful. Whereas before, you couldn't. Okay, so let me stop there. So there you can see a lot of how network connections have a huge effect in many different kinds of effect. Cascades, network benefits, and the long tail. Okay, so let me stop there. Thank you.